Welcome to today's paper reading. Today's paper is titled, Self-Supervised Video Desmoking for Laparoscopic Surgery. This paper was published on AR14 by Renlong Wu and colleagues from Haobin Institute of Technology. The SelfSVD method leverages clear pre-smoke frames to supervise other smoky frames, making self-supervised video desmoking feasible in real-world scenarios. To enhance desmoking performance, a masking strategy and a regularization term are introduced to prevent trivial solutions. Additionally, a real surgery video dataset has been constructed, which includes various smoky scenes. Experimental results demonstrate that SelfSVD can more effectively and efficiently remove smoke while recovering more photorealistic details compared to state-of-the-art methods. Surgical smoke is generated during surgery due to the activation of high-energy devices, leading to the destruction of proteins and fats and the evaporation of liquid water. This smoke obscures tissue details, diminishing the quality of laparoscopic imaging and impeding surgeons' ability to make informed decisions. To address this, post-processing laparoscopic images for desmoking has become an effective method. Additionally, the use of pre-smoke frames and self-supervised video desmoking techniques are being explored to improve visibility during surgery. Figure 1 presents a comparison between surgical smoke and atmospheric haze. The top row shows degraded images affected by each type of smoke, while the bottom row displays their corresponding clean reference images. The figure highlights that while both types of smoke share some similarities, they differ significantly in terms of local homogeneity and the ability to be physically simulated. Atmospheric haze typically follows the atmospheric scattering model and is locally homogeneous, whereas surgical smoke is more diverse and includes elements like mist, droplets, and streaks, making it difficult to simulate accurately. Traditional approaches to surgical smoke removal have relied on the atmospheric scattering model, which often results in color and structural artifacts. More recent learn-based methods have utilized convolutional neural networks, CNN, and vision transformers, with notable examples including modifications to the UNet architecture and encoder-decoder structures. Despite these advancements, a significant challenge remains the domain gap between synthetic smoke simulations used for training and real-world surgical smoke, leading to issues with generalization to actual surgical scenes. The proposed SelfSVD framework employs self-supervised learning by leveraging pre-smoke frames as supervision. This approach aligns frames using optical flow to prevent blurry results. Additionally, the framework takes the pre-smoke frame as a reference input to enhance smoke removal, mitigating errors in optical flow estimation. The network architecture is designed to include a feature encoder, a masked ref generator, an alignment module, and a fusion and reconstruction module to process surgery videos online. Figure 2 illustrates the process of handling the ITH smoky frame C in the context of self-supervised surgery video desmoking. The pre-smoke PS frame SBS is utilized as both a supervision tool and a reference input. To prevent trivial solutions, a masking strategy involving the masked ref generator, as depicted in Figure 4, and a regularization term defined by equation 10 are incorporated. Additionally, temporal features from previous frames, denoted as high-1, and those for subsequent frames high, are leveraged to enhance the desmoking process. This approach aims to effectively address the challenges of real-world surgical smoke removal by leveraging internal video characteristics and temporal information. Figure 4 illustrates the structure of the masked ref generator, which plays a crucial role in the video desmoking process. The mask generator is designed to create a mask me, which is then utilized to produce masked reference features for FI. This masking strategy is essential to prevent the output contents from being inconsistent with the smoky inputs. By excluding certain features from the reference, the model can focus on the relevant clean information, thereby improving the overall desmoking performance. Figure 3 illustrates examples of trivial solutions that occur when the pre-smoke PS frame is used as a reference ref input without proper alignment. The imperfect optical flow estimation between the ref and the smoky frame leads to these trivial solutions, as highlighted by the yellow arrows. The yellow lines in the figure mark the same positions where these issues arise, indicating areas where the model fails to correctly align the reference information with the smoky frame, resulting in overfitting to the reference and producing inconsistent outputs. Figure 5 illustrates the process of enhancing the PS frame, SPS, as supervision. Initially, SPS is considered a frame with less smoke and is fed into a pre-trained SelfSVD model, resulting in a cleaner output S*operator PS. This improved output, S*operator PS, is then utilized as enhanced supervision to fine-tune the SelfSVD model using the LREC and LGN losses, effectively replacing SBS with S*operator PS in the equations 5 and 11. This fine-tuning process yields an improved model named SelfSVD*operator. This approach ensures that the model is trained with more accurate supervision, leading to better performance in subsequent tasks. The SelfSVD dataset was constructed by collecting laparoscopic surgery videos from 40 patients. This resulted in 486 video clips, each with a resolution of 1080 by 1920. The frames were selected manually, focusing on the moments when high-energy devices were activated. The preceding frame was designated as the PS frame, and several subsequent frames, until the smoke was nearly dismissed, were considered smoky frames. The dataset is divided into 416 clips for training and 70 clips for testing, covering a variety of real-world surgical smoke scenarios. In this section, we discuss the experiments conducted for optical flow estimation. The method adopted for this task is detailed, along with the dataset used and the evaluation metrics employed. The experimental setup includes the hardware configuration, software environment, and key training parameters. Finally, the results are analyzed, comparing them with baseline methods, examining error sources, and highlighting performance improvements. The ablation study focuses on the training details, optimization strategies, and model variants. During training, patches are randomly cropped and augmented with random flips. The batch size is set to 4, and the patch size is 256 × 256. The model is trained using the Atom Optimizer with beta 1 set to 0.9 and beta 2 to 0.99 for 100,000 iterations. A cosine annealing strategy is employed to steadily decrease the learning rate from 1 × 10 to the power of -4 to 1 × 10 to the power of -7. Additionally, the study examines the performance of SelfSVD and SelfSVD* models, as well as their lightweight versions, SelfSVDS and SelfSVD*S. Figure 6 presents a qualitative comparison on the SelfSVD dataset, highlighting the effectiveness of our methods in generating results that are more consistent with the PS frame. In contrast, the compared methods often introduce color distortion, over-smoothing, or smoke preservation in their results. Our methods, however, are shown to remove more smoke and restore more details that align closely with the PS frames, demonstrating superior performance in smoke removal and detail restoration tasks. Figure 7 illustrates the qualitative results of using the PS frame as a reference, ref, input in the desmoking process. The figure compares the outcomes of the process with and without the ref input. The inclusion of the PS frame as a ref input results in a significant improvement in the quality of the desmoking process, as evidenced by a 0.67 dB increase in PSNR. This improvement is particularly noticeable in the removal of smoke, which becomes cleaner, and in the recovery of finer scale details, especially in areas with dense smoke. The figure visually demonstrates that the use of the PS frame as a ref input not only enhances the overall quality of the desmoking process, but also ensures that more accurate and detailed results are achieved. Figure 8 illustrates the effect of different strategies to avoid trivial solutions in the context of video desmoking. The figure shows that naively inputting the PS pre-smoke frame as a reference leads to trivial solutions, marked with yellow boxes in B. When using the masking strategy, mask, alone, it may generate artifacts around high-energy devices, as highlighted in C. On the other hand, using the regularization term, reg, alone may leave traces of high-energy devices from the reference, as shown in D. The combination of both strategies, however, produces better results, as evident in E. Table 1 presents a quantitative comparison of various desmoking methods on the SelfSVD dataset. The metrics used for evaluation include PSNR, SSIM, fade, NIC, and PI, with upward arrows indicating higher is better and downward arrows indicating lower is better. The table compares the performance of SelfSVD models against 16 state-of-the-art methods, categorizing them into unsupervised, unpaired, and self-supervised image processing methods, as well as self-supervised video processing methods. Additionally, the table reports the number of model parameters, flops, and inference time per frame for each method, providing a comprehensive view of their efficiency and effectiveness in desmoking tasks. Table 2 presents the results of ablation studies focusing on the reconstruction loss LREC. The table compares different methods of calculating LREC, including no loss, none, a naive one loss, the Kobe loss, aligning SBS with I, and aligning I with SBS. Each method is evaluated using several metrics: peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, frequency-aware deformation error, fade, naturalness image quality evaluator, NIC, and perceptual index, PI. The best performance is achieved by aligning I with SBS, which yields the highest PSNR and SSIM values, and the lowest fade, NIC, and PI values. Table 3 presents the quantitative results obtained when different references, ref, are input into the system. The references tested include none, no reference input, first smoky frame, and PS frame. The performance metrics reported are peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, frame aesthetic distance estimation, fade, naturalness image quality evaluator, NIC, and perceptual index, PI. The results indicate that the PS frame reference yields the highest PSNR and SSIM values, suggesting better reconstruction quality compared to the other references. The Laparoscopic surgery video desmoking, SelfSVD, dataset presents a significant opportunity for future research. Extensive experiments conducted by the authors demonstrate that SelfSVD outperforms current state-of-the-art methods both in quantitative and qualitative measures. This dataset and the SelfSVD method can be instrumental in improving surgical techniques and advancing the field of laparoscopic surgery. This research was partially supported by the National Natural Science Foundation of China under Grant number 623711164 and Grant No. U22B 2035. The authors are affiliated with Haobin Institute of Technology, Southern Medical University, and Hong Kong Polytechnic University. For further inquiries, please contact the corresponding authors at the provided email addresses. Thank you for watching.